Yeah, you asked me about two body interaction.
Sir, yes, three body BVL.
Yeah, two body and three body, right?
Yes, sir.
Three body interaction. So basically, there are only two body and three body, because if it is one body, then there is no tribology, right?
Yes, sir.
So yeah, so two body we will call when two surfaces are in contact here, but there is no third, there is no other thing. So it is possible that two surfaces are sliding without the intervention of any third particle or third body. Okay, so for example, very long back, some theory were proposed that two material, let's say I've got one material like this and another material, these circles represent atoms or molecules. Okay, so let's say this is interacting on this one. So there will be interatomic forces, right, acting between them. So some forces will be acting. So that means this, even at atomic scale, this atom is not even touching the other atom, but it is following this and experiencing the interatomic forces, and that forces are giving the friction. So we have to apply some friction, we have to apply some force to overcome friction, but they are not even in contact with each other in true sense, in a very atomic scale level. Okay, so this is a purely two body interaction. There is no third body interaction here. All we have is the intermolecular forces that are acting here between the two atoms. So this is a good example of two body interaction. This is also known as Prandtl and Tomlinson model. And actually this model was one of the way to explain friction, why there is friction between two materials. It is because the two materials have atoms and molecules, and these atoms and molecules will interact with each other. Okay, and this interaction will require some force. So this kind of interaction will lead to zero wear or no wear situation. Okay, and in a macroscopic world, if we have got two surfaces, let's say two steel, two metals or polymers, and these are two different solids and they are interacting. In the beginning, it will be two body interaction, because in the beginning, right in the beginning, there will be no other material available here. Okay, let's say dry contact. So it will be two body interaction. But in real practice, it can never be two body interaction, or it can hardly be two body interaction. There will be always third body present. So in the liquid lubrication, we can say liquid is the third body. And in dry condition, we can say, for example, a transfer film will be formed, okay, which will act as third body, or after wear some oxides will be formed, which will be third body. In lubricated sliding, there will be some boundary lubricants, boundary film formation. So all these are the third body, part of the third body. So almost nearly no tribological interaction is two body in practical sense. Okay, but two body interaction is possible in limited cases, in few cases. Okay, so this is the difference between two body interaction and three body interaction. Is that okay, Chandan? Have you understood?
Sir, you told in previous lecture that when two body, when the wear happening between two body, then wear debris produced, and that wear debris again corroding the surface of the material.
Yeah.
So it acts as a third body.
Right. So this is also the third body. So wear particles are also the third body. So yeah.
Sir, in two bodies, sir, when the wear, because when two body interacts, there is always a chance of wear, sir.
Yeah. So two body interaction will change to three body interaction very
Yes.
soon. Okay. So
Yes.
we may start as two body interaction, but it changes to 3-body interaction because there will be some wear debris particle formation, right? So either we put the third body by ourselves, for example, let's say lubricant or some
Any
powder,
abrasive,
yeah,
any
or
abrasive.
maybe abrasive, yeah, abrasive particles. Maybe it is coming from outside. Let's say it is coming from the dust. Or sometimes we may use powder as a lubricant. So powder can also be used as a lubricant. So that is also third body. But third body can also be produced by debris. So debris is the third body. So because of wear. So 2-body interaction changes to 3-body interaction. Okay, because of the wear debris. And sometimes we start with the 3-body right in the beginning. But 2-body as a concept, we can understand that 2-body interaction is when there is no other material involved.
Yes.
So is that
That is
clear now?
ideal condition, sir. But
Yeah,
in
ideal
practical
condition.
condition, this 3-body
Right.
we are happening.
Yeah. In fact, if you can reduce the coefficient of friction to very, very low value, then 2-body interaction is the best. So right. Okay. So last time we were talking about this friction reduction solution. So we have to understand very clearly what are different methods of friction reduction, because friction reduction is the one of the major part of tribology or tribological system design, and the second part is how to avoid wear. So both solutions are together because friction and wear are interdependent. In a sense, we can say that high friction leads to high wear. So lubrication methods we have talked about, and different different kinds of lubricants. So we need to study these oils and greases, their chemistry and viscosity, and how the viscosity will change with temperature, how the chemistry will change with temperature. So all are extremely important in these cases. So therefore, I said right in the beginning that tribology is very interdisciplinary. So tribochemistry it is called. Chemistry, which means whatever the chemical actions are happening at the interface is known as tribochemistry. There is also another term called tribophysics. So all these are very much interconnected. Bearing materials, we talked about different types of bearing materials, and very, very important ones are, first is AISI 52100, which is known as bearing steel. So there is a history of how this bearing steel was developed, but today bearing steel is used for all kinds of bearings, and this bearing steel has got high carbon, and it has got lots of chromium. So chromium is 1.3 to 1.6. Other than that, it has got manganese and silicon and so on. So last time there was question that can we use stainless steel, but actually we do not use stainless steel, even though stainless steel has got high hardness. Some of them has very high hardness, and stainless steel is corrosion resistant, is very tough. So all kinds of good properties are there. But if you think about the cost, the bearing steel will be cheaper because it has got the only expensive alloy is chromium. But stainless steel has got many other alloys. What are the main alloys of stainless steel?
Carbon and iron.
Carbon and iron, okay, but there are some other elements which make it stainless. Otherwise, it will be a normal steel.
So some of the manganese and titanium.
Yeah, those elements can be there in small quantities, but you should remember that stainless steel has got two very important alloying elements, chromium and nickel, and both are quite in high proportion, very, very high proportion. So therefore, chromium and nickel, and that makes stainless steel very expensive. So here in bearing steel, this one, you see the chromium percentage is not very high, although it is there, but not like 5-6% or something like that. So you can check the chemical composition of stainless steel, and you will find that chromium and nickel are very in high proportion. Okay, but it is not there in bearing steel. So that's why cost-wise bearing steel will be cheaper, but performance-wise it is very high hardness. It has a high hardness, and it has got very high toughness. These are the two most important ones. Okay, other properties like corrosion resistance also is good because of presence of chromium. Okay, so this steel is used for its bulk properties, not for its surface property. But there are other kinds of bearing materials which are used for their surface properties. For example, Bharat material, Bharat metals. I think it has got spelling mistake, maybe double BIT. And among polymers, PTFE is used. So these are some of the materials, but of course there are many other materials which are used for their surface property. So the important thing is to how to make a good bearing material by designing its bulk property and the surface property, and that's why the case of composite materials come into picture, because through composite materials we can actually design the bearing material themselves. So in the case of plastics, we always go for composite materials, and even for metals, if we can go for composite materials, it will be much better in its properties. Okay, so we will talk about these things. There is one more which is important we should know is bronze. Bronze. It is not brass. Brass is sometimes or many times maybe are used for, because it is brass is cheaper than bronze, but the bronze is the good tribological materials. Brass is not that good. Okay, and we will talk about materials aspect, the coatings and so on later in this course. And another is about bearing design. So bearing design is based on many theories. There are many theories, and one very important one is Reynolds theory. Okay, Reynolds theory, because this theory gives us design aspect for fluid film bearings, and also for rolling element bearing, because they are in the what is known as elasto-hydrodynamic lubrication. So we will talk about that one. And the most important are how to balance the stresses and speed, load, sliding and rolling elements. So these are all balanced by proper bearing design. So bearing design is a very important aspect of tribological systems design, because only applying lubricant will not help. We need to control the stress. That means we need to reduce the stress. Often it is to reduce the stress. We need to keep the speed within certain limits, because at high speed you will have temperature rise, right?
We just have a few more points to quickly.
So because of temperature rise, again you will have lubricant degradation and so on. Okay, then you have to ensure that sliding contact is reduced and you use as much as rolling elements. Okay, that is another thing. But of course there is a cost is involved. So given a cost, we will try to sliding element will be cheaper, but rolling elements will be more expensive. But depending upon our industrial application, we have to select any of these things. So right now, based on many design rules, there Reynolds theory gives you more theoretical analysis, but they are more practical rules. Practical rules, and in this tribology, actually there are many practical rules. That means people have conducted some industrial based experiments, and they have devised some rules, okay, which are based on empirical relation. So we should know all those kind of practical rules so that we can select a proper bearing design. So all we need to know is how to select proper types of bearing so that we can manage our stress and speed and temperature. Okay, so possible tribological solutions. So obviously we are very much focused on different types of solutions for tribology. So here let's discuss them in general. Okay, so the very first one here we have got which is dry contact, and we have talked about this dry contact in quite great detail. So for dry contact, either you change the interface by providing a certain type of coating or a thin layer to separate the two materials. So this can happen. So for example, some coatings are applied. Can you name any coating which can be used for tribological purpose?
Diamond DLC.
DLC, okay. Any other DLC and any other? There's one quite common one.
Not recall, sir.
Okay. Have you heard of Teflon coating or PTFE coating?
Teflon polymers.
Yeah, polymer or PTFE coating. They are same thing. Teflon is the commercial name of PTFE. PTFE is more chemical name.
Yes. Non-stick pans are of Teflon.
Sorry, could you say again?
Non-stick pan.
Yeah, non-stick pans. Yeah, non-stick pans that we use in our kitchens are also Teflon coated or PTFE coated. So the same PTFE can be coated on any bearing surface, and actually you can solve this problem just in dry condition. And of course, Bharat material also can be used. Okay, so these kind of solutions can be used for dry contact, and often we prefer dry contact because we do not want to have liquid lubricants. As I said before, that liquid lubricants are very toxic in nature, and if we are dealing with food items especially, you want to have dry contact. Or if you are dealing with vacuum or even radiation, in all conditions you need to have dry contact. So this is a very important one, and here also there is a lot of tribological design rules that we have to understand. So in the dry contact, we should never use two metals together. Okay, never use two metals. Okay, because metals can never give you low coefficient of friction. It will lead to very high friction, no matter what. You know, even if you use bronze and steel, still you will have high friction and lot of wear. So always metal plus non-metal, and among non-metal plastics. Okay, so either in the form of a coating or in the form of a kind of sleeve, or you change the material. The bearing part can be made into plastic. So these are the kinds of solutions for dry contact. The next two, these are for fluid film. So among fluid film, we can include both liquid as well as gas or air. Okay, air is cheaper, so air will be used, and liquid will be many different types of liquids. Okay, so these are the two types of fluid film bearings. In both cases, fluid will be used, but in this case, the the shaft is rotating, and because of this rotation, a kind of hydrodynamic pressure is built up here. So hydrodynamic lubrication it is known as. So hydrodynamic pressure is built up, and this pressure will be maximum at some point here. Okay, again it is decided by the Reynolds theory. So at some point it will be maximum, and the pressure will be something like this. Okay, so that means at some point there will be maximum pressure, and if you take the mean pressure of this one, so the mean pressure will all act in this direction, and your load shaft is supporting some load, right? The shaft will always have some load. So the load is from this. Okay, so this pressure will actually cause this force in this direction, which will carry the load. So this hydrodynamic pressure is enough to carry the load, and this is what happens in this kind of lubrication. So which is also known as journal bearings. So this part is known as journal, and this is the bearing part, or you can call it bearing and the shaft. But the most important is this one. Okay, now here just one thing is that this thickness, the fluid film thickness, which we are showing here, both cases has been exaggerated. The actual thickness will not be so much. Just for the drawing purpose, we just increase the thickness here just to show this one. But in actual practice, this thickness will be only in the range of 10 to 100 micron. Not so much compared to the shaft dimension or the bearing dimension. So the most important part is that the hydrodynamic action, because of the rotation, the pressure is built up, and this pressure will support the load. Okay, so all around the pressure will be high, but pressure will be maximum here. So this is the main principle that we learn in hydrodynamic lubrication, and also then it goes on to EHL, which is elasto-hydrodynamic lubrication, which is just a subset of hydrodynamic lubrication. So we will study about the Stribex curve and show how, in what condition EHL will be formed and in what condition HL will be formed. The second part is hydrostatic. So hydrostatic by nature, that means something is static, and because of the presence of fluid, or in the case of liquid it is called hydrostatic, but if it is gas or air, then it is called aerostatic. Okay, that means pressure is built up in a static condition. So here you see pressurized lubricant supply. So lubricant is being supplied from these 4 ends or maybe more ends. Okay, and it can be, it doesn't have to be always liquid, it can be gas as well. So because of this pressurization, this pressure will actually support the load. So this shaft is carrying some load. So this load will be supported by this pressure inside, which is hydrostatic pressure, and it has been created by externally pumping the gas or pumping the liquid. Okay, so you need a compressor outside. Okay, so you need to have the compressor so that you can create that kind of pressure inside. And so there are many such kind of air bearings, which are known as air bearings. So air bearings are basically where air is used as a fluid, and liquid pressure bearing also you can use. Okay, so the difference between these two is that the way we create the pressure. Okay, but both are liquid film or fluid film lubrication method. Okay, so but this can be a little bit more expensive because we need a compressor. We need externally, we need to install a compressor to create this kind of pressure. Another problem with this one could be that this kind of lubrication method or tribological solution may not be used in a mobile application like transportation. You may not be able to use this in cars or trucks or trains, because it requires much more equipments, and that equipments will be also heavy, will carry some weight, and so therefore the overall efficiency will be reduced. You are saving on here, but you are spending money and energy on something else, on carrying a very heavy equipment with you. So each has got its own advantage and disadvantage. So therefore, in the design process, we have to understand the principles and we have to make some decisions. So this is very, very important. We have to make an overall decision on how to decide which type of tribological solutions we need. Okay. In a already conventional engineering machine, the solutions are quite obvious because the solution will be always there and you know what to do. But in a new situation, when you are designing a new machine or totally new concept, then you need to understand all these things so that you can take a decision on which tribological solution you should try. Okay, so the next here is the rolling element bearing. So rolling element means something is rotating here. It can be ball or it can be pins or cylindrical rollers bearing. So you see the rolling friction is lower than sliding friction, is far less than sliding friction. This is the concept. So this is very, very important to know, and we have already discussed why rolling friction is less than sliding friction. So for all cases, our aim is to convert sliding friction into rolling friction. So for example, that is how the wheel was invented, right? So if you talk about, maybe you don't remember, but long back we used to have luggage without wheel. Do you remember?
No, sir.
No. Yeah, because you have never seen that period of time. But when we were children, our luggage, like all these kind of suitcases, never had a wheel. So traveling was so cumbersome, so difficult. So you imagine, on a platform, even on a platform, of course, forget about on the roads, you have to carry physically. So either there is a handle here, you have to carry the suitcase, and if the suitcase is very big, it will be very heavy. Or in some cases, you just slide it, like you just have something to pull and keep pulling. Again, there will be a lot of friction here. Okay, so traveling was not that fun as it is today, and the reason is today our luggage has got wheel. Okay, so we never even think about how difficult it is to carry a luggage. And you see in all of our railway stations, we have so many porters, right? And today you may say that because of these wheels, many of those porters are losing job. Have you seen the porters not getting any job because people bring their suitcases with wheels, right? But in olden days, it was not an option. We had to hire a porter who can help us to carry the luggage. But today, because of wheel, we don't have. So you can see that this very, very simple thing, you may think it is very simple, but this tribological solution has changed many things. It has changed the way we travel. Now traveling is more fun. Before it used to be always carrying a lot of loads. But in this kind of solution can also affect somebody else. And it is affecting the job of the porters because porters are not getting a job. People don't hire them.
Sir, can you give example of a that dry friction lubrication. In which, sir, we use PTFE.
Okay, so see, the PTFE is a very unique.
Because sir, inner body is rotating, no?
So sorry, what is your question?
Sir, any example of this types of lubrication, dry lubrication?
Dry lubrication, yeah. As I said, PTFE coating is provided in many of this kind of plain bearing. These are known as plain bearings. So, of course, non-stick pan is also an example we talked about, which you can see in the kitchen, that we have got pans with PTFE coating all around, okay, which reduces the stick.
Sir, I think in this picture, inner body is rotating.
Yeah, in this one, inner body is rotating, yes. There are other example of coating, for example, in magnetic hard disks. The disk is coated with DLC and some lubricant. Okay, first is DLC and some lubricants, which is also a kind of PTFE, PFPE, another material. So in magnetic hard disk, where we save our data in our computer, so there is a disk and there is a slider here. The slider reads and writes the information while the disk rotates. So the problem is the tribological interaction, and therefore we use this kind of coatings. So as we go along, I will give you some more examples of these coatings, but coatings are applied. And in fact, these coatings are applied even in conjunction with these fluid film lubrication. So that is another thing.
Yes.
Yeah. So there are many examples, and I will talk about those later. PTFE has got high wear. So the wear rate is very high, and therefore PTFE cannot be used as a tribological material, but it can be used as a coating. And
also it is act as a brittle material, like crack, get fracture. Yes, it is ductile material. It is highly ductile material, so therefore it will not crack. It acts as a brittle material. Yeah. Because in kitchens. Yeah, it is not brittle material. PTFE. What did you say? Could you say again? Generally, we see that without any elastic deformation, it got crack and worn out. Yeah, after repeated use, yes. But when you have a new pan and it has got the coating, it doesn't get removed so easily. So PTFE by nature, it is very ductile. So it will undergo plastic deformation, but after repeated use, because of the thermal action, its molecules have changed. So it has degraded, and that is a form of thermal degradation. Yes.